Tonight, we're taking over the telescopes of La Palma. Welcome to the sky at night. The Liverpool telescope has a mirror 2 meters across. What makes it really remarkable is that it's completely robotic and available to astronomers all over the world. The nice thing about the Liverpool telescope is that you can control it from anywhere with just a web browser. And so tonight, we've decided we're going to look at the Waterfall Nebula. It's 10 o'clock and we've now got the results from last night's run on the Liverpool telescope, including our observations of the Waterfall Nebula. So let's have a look and see what we've got. All of our images are here. Let's start by looking at the blue image that we took. In blue light, the image is pretty disappointing. You can only just make out the faint outline of the nebula. But when we look at the image taken with a filter that lets through light from hydrogen gas, we see the fine detail and the waterfall comes to life. But an individual image can't tell you too much. What we have to do is put them together to create a colour composite. So let's do that. There we go. It's actually a beautiful image. It's easy to see how the structure got its name. There's even a splash of hot green gas at what appears to be the bottom of the waterfall.
The mirror of the Isaac Newton telescope is 2.5 meters across. That's about 100 inches in old money. And it's got a field of view of 1/2 degree across on the night sky. That's about the size of the full moon. That allows us to survey huge areas of sky at a single time and look for comets, asteroids, and anything else we want to observe.
41.3.
41.3.
10 plus 5.
05.
18.
18.
45.
45. J2000. And we're on our way.
323P has only been seen from space by the solar observation satellite SOHO, and it's unclear if it's an asteroid or a comet.
You can see it right here, this white dot as it goes through. And it passes through a little bit more than once every 4 years. And we're trying to study it from the ground. It's never been seen from the ground before. And we're trying to determine if it's a comet or if it's an asteroid. Because when it comes so close to the sun, more or less anything would look like a comet. So we're studying it here today to determine what it is.
They're using a piece of software designed to track the movement of comets and asteroids.
I think this is more than 12.
If they're searching the right part of the sky, the object should leap out of the picture as a single bright point of light, while the stars and galaxies in the background remain blurred.
Yeah, that's a beautiful image. There's a rogue asteroid for you. Okay, so we were asked to image a definite asteroid, in fact a rogue asteroid, one that comes close to the Earth. And so we've taken these data of one called 1995 CR, and in these images that I'm blinking through, you can see it moving against the background stars and galaxies. Now, from our brightness measurements, we know that this is about 100 meters across, and we also know from its orbit that it can come within 2 million kilometers of the Earth. So if it ever hit us, it could easily wipe out a city. Now, we know we're safe from this asteroid for the next 100 years, but to be sure on a longer time scale in the far future, we need a better orbit. So we needed to take more data for this asteroid, so thanks for the request.
What I find fascinating about telescopes like these is for all their huge mirrors and complicated optics, they're not much better in terms of magnification than your best amateur telescopes. But where they do gain is in terms of light gathering power. Because when you've got a mirror that big, you can see faint, distant objects so much more clearly. So the telescope is now pointing.
We're now right there.
So are we actually getting an exposure as we speak?
It's reading out.
Actually reading out.
Okay, so you've got the exposure.
In the very
Yes.
few seconds, we're going to see the very first.
It will appear. It's beautiful. At a mere 30 million light years away, the galaxy is too big for Grantacam to image in a single frame. And it takes a range of exposures at different wavelengths of light. Those are the details we can make out on the first view. But to get the best image of the galaxy, we needed to process all the images we took that night into a single composite. This is the finished image. A stunning view of galaxy NGC 891, taken by the Gran Telescopio Canarias.
Now the pattern of lines remains constant, but the whole spectrum shifts as the star moves. The spectrum becomes more red when the star is moving away from us, and more blue when it moves towards us. And it's that red-blue pattern that indicates the presence of a planet around a star. And that is what the team here are hoping to find. In the control room, the Italian team trained the telescope on individual stars and take their spectra. The HARPS instrument is so sensitive that it can detect if the star is moving towards or away from us at speeds as low as 1 meter per second. That's walking pace. But one spectrum isn't enough to reveal the presence of a planet. The same star must be observed, and its rate of motion measured again and again over many nights. These are results from a star in the Beehive cluster that was observed many times between 2013 and 2015. So that's it. After all that work, 70 nights of observation over 2 years, we're left with a graph. But it's a good graph. You could see from the way the star moves, this back and forth, it's this pattern that tells us there's a planet there. And so we can't get you an image of an exoplanet, I'm afraid, but I'm telling you, this is just as good.
What I find fascinating about telescopes like these is for all their huge mirrors and complicated optics, they're not much better in terms of magnification than your best amateur telescopes. But